So we're going to get some practice with our work, power, and energy equations that we've been using. The first thing you need to know is there's about 5 equations that we need to know for this unit. So we'll go ahead and just kind of make a cheat sheet of those. So the first equation that you need to make sure that you know is that work is equal to force times displacement. The next equation that we need to know is that power is equal to work divided by time. Our third one, this is where we get into energy. We can say that our kinetic energy is equal to 1/2 mv squared. It's important to note that only the v is squared in this equation. Our fourth equation is going to be the first type of potential energy. So mass times gravity times height. So that's our gravitational potential energy equation. And our last one is going to be also potential energy, but this is going to be the potential energy of a spring, which I'm going to signify here with this S. And that equation is just going to be 1/2 kx squared. So remember, this is where this k stands for constant, x is for displacement. So this is only when we're dealing with like a spring or a rubber band. We can also talk about the units that each of these are measured in. So for instance, if we're talking about work, that's measured in joules or just a capital J. Power is measured in watts, and any type of energy is also measured in joules. So the only thing that's going to be measured different here in these equations is going to be our power equation, which is measured in watts. All right, so let's look at this first practice problem. We'll come back to these equations. It says, after scoring a touchdown, Paul, an 84-kilogram wide receiver, celebrates by leaping 120 centimeters off the ground. How much work was done in the celebration? So the first thing we need to do is identify any important information or any number in any unit. So I'm just going to circle every number and unit that I see, and then I'm just going to underline what I'm looking for. So now I'm going to write out my list of givens. I'm going to say that anytime I see kilograms, I automatically should think that that's going to be the mass. And then anytime I see centimeters, I know that's going to be a type of distance or displacement. But you should also recognize that something's wrong with that being in centimeters. We know that things should be measured in meters. So we need to convert this from centimeters to meters. There's multiple ways to do it, but you could also do the King Henry died by drinking chocolate milk, which means we're going to move that decimal place 2 places to the left. So we're going to end up with 1.2 meters, and we are looking for work. So if we go back to our 5 equations, we need to pick an equation that will help us solve for work. All right, so we're going to pick this first equation. We're going to say that work is equal to the force times the displacement. So we can say we know our displacement, but we don't know our value for force. So how can we figure that out? So if we were to draw a free body diagram to help us visualize this, we know if we're jumping off the ground, we're probably going to have a force of gravity always going down and our applied force going upward. Since it doesn't mention that we're accelerating or anything, we're going to consider these forces to be balanced, which means if we can solve for one, we can solve for the other. So we can say that to solve for the force, we're just going to do mass times gravity, or mg. So this equation, which most of the time it will, is going to become work equals mass times gravity times displacement. And then we can see that we have everything we need because we know our mass is 84, we know gravity is 10 or 9.8, and our displacement is 1.2. So if we were to multiply all of that together, we should get 1,008, and remember we measure that in joules, and that's going to let us know how much work is done during the celebration. All right, let's take a look at another one. We'll take a look at one that requires us to use our energy equations. All right, so what about, or we'll go ahead and do power. Let's look at number 3. So number 3 states, an elevator lifts a total mass of 1,100 kilograms, a distance of 40 meters, and 12.5 seconds. How much power does the elevator demonstrate? So let's go ahead and identify everything that's important and underline what we're looking for. So if we wrote out our list of givens, we could say our mass, we know kilograms means mass. We know meters, going to be like our distance or displacement. And we know seconds is going to be a type of time. And we're looking for power. So if we go back to our list of equations, we can see there's only one equation that uses power, which is our second one, which says power is equal to work divided by time. So we're just going to say power equals work over time. So we have a time to plug in, but we don't have a work to plug in. So we're going to have to calculate our work. So we could say we know work is equal to force times displacement. Since we're being lifted upwards, we know that if we think back to the free body diagram, we know we're going to have gravity going down, and we're going to have like a lift force, or we'll just call that an applied force. And since it doesn't say we're accelerating, we're going to assume they're equal, so if we can solve for one, we can solve for the other. So we're going to end up with, again, that mg times d. So that means we're going to have our 1100 times gravity, which is 10, times our displacement, which is 40. That out, that should give us 440,000 joules. And so now we're just going to plug that in the equation and divide it by time, which is in seconds. So we should end up with 35,200, and since we're doing power, it would be watts. All right, so now I want to look at number 4, because this one's going to take care of our kinetic energy and potential energy, or our gravitational potential energy. So it says a 20-kilogram rock is on the edge of a 100-meter cliff. A wants to know what's the potential energy. So again, we're just going to identify that important information. We're looking for potential energy. So I'm just going to list that here. Kilograms we know is mass. Meters is going to be any type of distance. And we're looking for potential energy. So now, since we're not involving a spring or rubber band, we know we're going to have to use our gravitational potential energy equation, which on the list we made would be number 4. Remember, this one is the fifth one is only used if there's a spring. So we're going to say PE equals mgh. So we have a mass to plug in. I've said distance, but distance and height are going to be the same thing. So we'll plug in our 20. We know gravity we could say is 10, and our height is going to be 100. So we should end up with 20,000. And since it's just a type of energy, it's measured in joules. On part 4, I know we just solved that. We said that this was going to be 20,000 joules. But let's think about the relationship between potential and kinetic energy. We know potential energy is at its maximum at an object's highest point, and kinetic energy is maximum at its lowest point. So let's know the kinetic energy, and it says just before it hits the ground, because if it was to hit the ground and it wasn't moving, we know that wouldn't be kinetic energy. But we can say that all the potential energy it starts with is going to be equal to all the kinetic energy it ends with. So for part B, we would just get 20,000 joules as well. But let's take a look at one that would require us to use our kinetic energy equation. So let's look at number 6. This one requires a little manipulation. So we see that we have 15 meters per second. It gives us a kinetic energy of 4,200 joules, and it wants to know the mass. So if we write out our kinetic energy equation, we got to think, how are we going to get that m by itself? So the first thing I want to do is get rid of that 1/2. Since we're dividing by 2, we're going to multiply both sides by 2. You'll get 2ke equals mv squared. And then to get rid of that v squared, we just have to divide by v squared on both sides since it's being multiplied. So we end up with 2ke divided by v squared equals m. And now we can just plug in our values that we had already pointed out. We can say 2 times our ke of 4,200 divided by our velocity of 15 squared. And if we put that in our calculator, we should get 37.3 kilograms. Remember, mass is measured in kilograms. The last one I want to look at is number 8. It says a spring scale has a spring constant. So anytime you hear spring constant or you see anything that's measured in newtons divided by meters, I automatically want you to think K as in constant. It is compressed 4.3 centimeters. What is the scale's potential energy? So we could say we're looking for the potential energy of something with a spring. We know our K, or our constant, is 450 Newton per meter. And we can say that our x, our displacement, is 4.3 centimeters. Of course, we need to do a unit check, and we see that we have meters and centimeters, so they need to be equal to each other. So we can convert this to meters pretty easy by, like we said earlier, just moving it 2 places to the left. So we're going to end up with 0.043 meters. Now going back to our equation, we're going to use the fifth one. This is only if we have springs or rubber bands, and we're just going to plug in our values. We know K is going to be our spring constant and X is our displacement. Only the X is squared in this equation. So we'll say PE of a spring is equal to 1/2 times KX squared. Plug in our values. We'll get 450 times 0.43 squared. And so our potential energy should come out being around 976.5 joules. Alright, so that should give you guys practice with all the equations, but just let me know if you need any more help. You guys can send me an email. But remember, the main 5 equations that we need to know, remember this one is only if we're dealing, number 5 is only if we're dealing with a spring or rubber band. Any other type of object, if we're calculating potential energy, we'll use number 4. Number 3 is the only equation we have for kinetic energy. Number 2 is if we're calculating power, and number 1 is for work. They all have the same units except for power, which is measured in watts.